In this last video of this lecture and the course, I'm going to talk about the other forms of learning that are less talked about. And the first of those learnings is called metric learning. If you remember, several times before I mentioned that most frequently used metrics of similarity between two feature vectors are Euclidean distance and cosine similarity. Such choices of metrics seem logical but arbitrary, just like the choice of the squared error in linear regression. The fact that one metric can work better than other depending on the dataset is indeed an indicator that none of them are perfect. The thing is that you can also create a metric that works better for your own dataset. It is then possible to integrate your metric into any learning algorithm that needs a metric, like k-means or KNN. But the question is, how can you know without throwing all possibilities which equation would be a good metric? Uh, do you remember this Euclidean distance between two feature vectors x and x prime? One way is to slightly modify this metric and make it parameterizable and then learn these parameters from the data. Consider the modification I just put on this screen. Here we have a matrix A, which is a D by D matrix. Let's say the dimension we have here is 3, and if A is an identity matrix, simply it will bring us back to the Euclidean distance matrix. But let's say if we want to try another A here, and then at another diagonal matrix like the one you see on the screen, then the different dimensions have different importance in the metric. And in this example, the second dimension is the most important in the metric calculations. More generally, if a function is to be called a metric functions of two variables, it has to satisfy these three uh, conditions: non-negativity, triangle inequality, and symmetry. I'm sure you have seen these functions these properties several other times in several different courses. To satisfy the first two conditions, the matrix A has to be positive semi-definite. I don't think you need to know what that is. Basically, that is an algebraic term. Uh, And for the third condition, we can also simply basically get the average of the distance between x and x prime plus x prime and x. So let's skip this mathematical algebraic part and get to a more user-friendly part with giving you an example. Let's say we have an annotated set X. To build the training data for our metric learning problem, remember, we have now some parameters in our metrics and we want to learn those parameters. So to build the training data for our metric learning parameters, we manually create two sets. The first set S is such that the pair of examples xi and xk belongs to set S if xi and xk are similar from our subject perspective. And this is the important point here. What we think are similar. Remember that we are building a metric projecting our view on similarity. So we put a pair of examples in S if we think they are similar. And similarly, we make another set D where we put the pair of examples there that we think are dissimilar, again from our subjective view. And then to train the matrix of parameters A from the data, we build a positive semi-definite matrix A and solves an optimization problem that you see here. And the solution to this optimization problem is found by gradient descent with a modification that ensures that the found matrix A is positive semi-definite. And we'll leave the description here of the algorithm because it's a bit more complex and involved. Just to let you know that this sort of learning is out there, this is possible, these are the steps. And I also should point out that one-shot learning with Siamese network and triple loss also could be seen as metric learning problem. Another sort of learning is learning to rank, and this is a supervised learning problem. Among others, one frequent problem solved using learning to rank is the optimization of search result returned by a search engine for a query. In search result ranking optimization, basically a labeled example in the training set of size n is ranked collection of documents of size r, and a feature vector represents each document in the collection. The goal of the learning is to find a ranked function f which outputs value that can be used to rank documents. Uh, Forgetting about what where thing that I said could be a bit, it could sound a bit complex. The whole idea is here to find a function that tell us how to rank certain documents. There are three approaches to solve the problem: pointwise approach, pairwise approach, and listwise approach. In the pointwise approach, what happens is that this approach transforms each training example into multiple examples, one example per document. Then the learning problem becomes a standard supervised learning, either regression or logistic regression. And in each example of the pairwise learning problem of x and y, x is the feature vector for some document and y is the original a score or synthetic score obtained from ranking. Uh, in For example, if we had already given a high rank to a Wikipedia page in some collection of documents, we would prefer not giving a high rank to another Wikipedia page for the same query. In pairwise approach, we also consider documents in isolation. However, in this case, a pair of documents is considered as one. Basically, given a pair of documents xi and xk, we build a model f which takes this pair as an input and output a value close to 1 if the first document should be ranked higher than the second one. The pairwise approach works better than the pointwise, but still this is far from perfect. The state-of-the-art rank learning algorithm is called Lambda MART that implements a listwise approach. In listwise approach, we try to optimize the model directly on some metrics that reflect the quality of ranking. There are various metrics for assessing search engine results, including precision and recall, and one popular method is mean average precision. I'm going to talk about that a bit later. And to define a map, let us ask judges to examine a collection of search results for a query and assign relevancy label to each search result. And the results could be binary or some scale. The higher the value, the more relevant the document is. And then let our judges build search relevancy labeling for a collection of, let's say, 100 queries. Now let us test our ranking model on this collection. The precision of our model for some query is given by basically the intersection of relevant documents and retrieved documents over the retrieved documents. And here by this colon and dot in between, I mean the number of something. The average precision metric is defined for a ranked collection of documents returned by a search engine for a query queue, as you can see here, where n is the number of retrieved documents, pk is the precision computed for top k search results returned by our ranking model, and rel of k is an indicator function equaling to 1 if the item at rank k is a relevant document, and 0 otherwise. And based on these, basically we define map. So these are our tools to get back to lambda mart. This algorithm implements a pairwise approach and uses gradient boosting to train the ranking function h of x that you see in this formula. And then the binary model f of xi and xk predicts whether document xi should be ranked higher than document xk or not, and that is given by a sigmoid with hyperparameter alpha. Again, as with many models that predict probability, the cost function is cross entropy. Remember that in gradient boosting, we add a tree to the model to reduce the error that current model makes on the training data. The classification problem, for example, we computed the derivative of construction to replace real labels with these derivative, and similar to all these, lambda mart works more or less the same, with one exception. It replaces the real gradient with a combination of the gradient and another factor that depends on the metric, such as map. And then this factor modifies the original gradient by increasing or decreasing it, so the metric value is improved. Okay, another learning approach, and this would be the final of this course, is learning to recommend. Learning to recommend is an approach to build recommender systems. Usually, we have a user who consumes content, and we have the history of consumption and want to suggest this user new content that they would like. It could be a movie on Netflix or a book on Amazon. Traditionally, there are two approaches: content-based filtering and collaborative filtering. Content-based filtering consists of learning what users like based on description of the content they consume. For example, if the user of a news site often reads new articles on science and technology, then we would suggest to this user more documents on science and technology. More generally, we could create one training set per user and add new articles to this data set as a feature vector, and whether the user recently read the new article as a label. Then we build a model for each user and can regularly examine each new piece of content to determine whether a specific user would read it or not. The content-based approach has many limitations. For example, the user can be trapped in the so-called filter bubble. The system always suggests to the user the information that look very similar to what she or he has already consumed. That could result in complete isolation of the user from the information and disagrees with their viewpoints or expands them. On a more practical side, the user may just stop following recommendations, which is undesirable. Collaborative filtering has a significant advantage over content-based. The recommendations to one user are computed based on what other users consume or rate. For instance, if two users gave high rating to the same 10 movies, then it is more likely that user 1 will appreciate new movies recommended based on the taste of the user 2 and vice versa. The drawback of this approach is that the content of the recommended item is ignored. In collaborative filtering, the information on user preference is organized in a matrix, then each row corresponds to a user, each column to a piece of content that user rated or consumed. And usually this matrix is huge and extremely sparse, which means that most of its cells aren't even filled or filled with a zero. The reason for such sparsity is that most users consume or rate just a tiny fraction of available content items, and it is very hard to make a meaningful recommendation based on such sparse data. Most real-world recommender systems use a hybrid approach. They combine recommendations obtained by the content base and collaborative filtering methods. Uh, I already mentioned that content-based recommender model could be built using a classification or regression model, that predicts whether a user will like the content based on the content's feature. Example of feature could include the words in the book or news articles the user liked, the price, the recency of the content, the identity of the content author, and so on. And I'm not going to dig further into this much more than this, just letting you know that there are two effective recommender system learning algorithms that are factorization machines and the noising autoencoders. And by that, I end up this part on other learning approaches. Hope you have enjoyed our experience throughout the course, and I wish you best of luck with your future career in machine learning or wherever you want to use machine learning again. Remember that as a machine learning expert in future, it is not only about what you learned in this course or any other platforms. Your most valuable skill is to be able to be adaptive, to find new solutions. What I taught you now could become redundant in a couple of weeks, in a couple of months, in a couple of years, because the science is improving so fast and in a rapid pace that if you want to stick your old knowledge, there is no way to get somewhere in this ever growing field of AI, machine learning, and data science. What you have to learn from this course and carry it with you is that there are approaches for solving different problems, and you already know the basic ones. You need to be able to expand on your knowledge. You need to be able to ask yourself questions. How do I improve on this algorithm that I use? And for that, you need to understand the working on each algorithm, so to know where you need to do tuning. And more than that, you should keep yourself updated with different architectures, different versions of the algorithms that are coming out, or altogether new algorithms that are coming out. As I said, your most important asset is to be able to ask the right questions, to know where to look for the right answer, to be creative, to be adaptive, and find your own personalized solutions for the problems. And don't be afraid. At the end, what we know is that always, always, always there is a solution for any question that you ask. And that is the most important thing. Don't get discouraged. Ask, dig, search, and you will find. And by that, I wish you all good luck and hope to see you all succeed in your career. Bye.